Hello friends, welcome back to my channel and welcome to lecture series on distillation. This is part number 5 of my lecture series on distillation. So far I have discussed fundamentals of distillation, material balance for distillation, one numerical based on material balance for distillation. Then I started discussing vapor liquid equilibrium as it plays a vital role in distillation. So in vapor liquid equilibrium, I discussed the basic concept of vapor liquid equilibrium, and in my previous video I discussed vapor liquid equilibrium at constant pressure. Vapor liquid equilibrium studied at constant pressure. So when vapor liquid equilibrium is studied at constant pressure, it results in what is called as the boiling point diagram. So in my previous video I had discussed boiling point diagram in details. For those of you who have not yet seen my earlier videos, I'm giving links to all those videos in the description section. You please watch those videos to understand the concepts. Also, do subscribe to my channel. Tell your friends to subscribe to my channel and hit the bell icon so that you'll be notified as soon as a new video is uploaded on this particular topic. Okay, so let us start the discussion. So this is distillation part 5, as I said earlier, and in this I'm going to discuss vapor liquid equilibrium. Okay, so vapor liquid equilibrium or simply VLE. In this particular lecture or in this particular discussion, we will understand the concept of distribution diagram. We will understand what is distribution diagram, how it is plotted, what is the significance of distribution diagram. To begin with, let me tell you, distribution diagram is one way of representing vapor liquid equilibrium. So last time we saw in last time I discussed a boiling point diagram. So boiling point diagram was one way of representing VLE, vapor liquid equilibrium. In the same way, distribution diagram is another way of representing vapor liquid equilibrium. So let us understand what this diagram is. So before that, I'll just show you the boiling point diagram. The boiling point diagram looks like this. I have discussed it thoroughly in my previous video. You please watch the video. So you have temperature plotted on y-axis and mole fraction of more volatile component plotted on x-axis. Mole fraction in liquid phase and mole fraction in vapor phase, both are plotted on x-axis. Okay, so we are talking about mole fraction of the more volatile component. So in our discussion we had considered a binary solution of A and B in which A was more volatile. Okay, so for that particular binary system we had discussed this boiling point diagram. Okay, now on the boiling point diagram, as you know, there are infinite number of tie lines. So boiling point diagram gives you tie line data, and on distribution diagram, whatever tie line data is obtained from the boiling point diagram, you can plot it in a different way. The tie line data is plotted in a different way on the distribution diagram. Okay, so distribution diagram basically is a plot of tie line data, but in a different way. Okay, so what is done in this? On the distribution diagram, mole fraction of A, that is more volatile component, mole fraction of A in the liquid phase, we denote that by X, and it is plotted on the x-axis, whereas mole fraction of A, that is more volatile component in the vapor phase, it is plotted on y-axis. Okay, so X, small x, which is mole fraction of A, the more volatile component in the liquid phase, it is plotted on x-axis, and mole fraction of A in the vapor phase, it is plotted on y-axis. So resulting diagram, whatever curve you get, whatever diagram is obtained, that diagram we call it as distribution diagram. Okay, so on distribution diagram, mole fraction of A, that is more volatile component, in the liquid phase it is plotted on x-axis, and in the vapor phase it is plotted on the y-axis. Okay, thus tie line, a particular tie line on this boiling point diagram, it becomes a point on the distribution diagram. So this is how the tie line data is converted into or this is how tie line data is plotted in a different way on the distribution diagram. So a tie line on the boiling point diagram, it becomes a point. Okay, so let us move ahead. So let us see how the distribution diagram looks. So you have x plotted on the x-axis, y plotted on the y-axis, and then for reference we are drawing this diagonal line over here. It is drawn for reference. The actual plot of y versus x is this red curve. This curve is called as distribution curve, and this diagram, we call this diagram as distribution diagram. Okay, so the distribution curve, the red curve, which is obtained by plotting x versus y, this distribution curve in this diagram, you can see it is lying above the diagonal line. The distribution curve is lying above the diagonal line. It is very much clear from this diagram. So what does it indicate? At every point on the curve, for this particular distribution curve, any point on the curve, at any point on the curve, y is greater than x. So you take any point on the curve. At that point, so value of y will be greater than x, and this is true for all the points that are lying on the curve. So if you have a distribution curve whose nature is like this, then this will be true. On curve like this, every y will be greater than corresponding x. So what is the understanding of this? This indicates that vapor phase, since every y is greater than x, the vapor phase is rich in the more volatile component. It is rich in more volatile component. That is, in other words, concentration of more volatile component in vapor phase is greater than that in the liquid phase. So at equilibrium, when you have a distribution curve like this, what can we say? At equilibrium, the vapor phase will be rich in more volatile component, and in order to have successful distillation, this type of distribution diagram is necessary. Okay, so a distribution curve like this is essential for successful distillation. Okay, let us now move ahead. Now just now I told to you that a particular tie line on the boiling point diagram, it becomes a point on distribution diagram. Let us see. So I have shown both the diagrams on this slide. So you have boiling point diagram over here and distribution curve over here. Now you just look at this tie line GF. So information of this tie line, when it is read on the distribution diagram, you just have a point. So tie line GF, it becomes a point over here. Similarly, tie line DE, it becomes a point on the distribution curve. Okay. Then let us understand. So you have this distribution diagram. We have just understood it, the distribution curve. Now let us see what is the effect of increased pressure on this distribution diagram. In my previous video, I have discussed effect of increased pressure on the boiling point diagram. Now let us understand what is the effect of increased pressure on the distribution curve. Okay, so the point is, if you increase pressure, with increased pressure, what happens? The distribution curve, it becomes smaller and it moves towards the diagonal. So these two effects are observed. If you increase the pressure, the distribution curve will become smaller and it will move towards the diagonal line. Okay. So let us understand. Now, if pressure, let us for example say the pressure is increased from P1 to P4, where if you are increasing pressure from P1 to P4, then P1 will be less than P2, that will again be less than P3, and P3 will be less than P4. Okay. Now let us say that this curve is obtained at a pressure of P1, and now we are increasing pressure from P1 to P2, and if you plot the distribution curve at that pressure, you get a curve like this, which has become smaller and it has moved towards the diagonal line. So this happens at increased pressure P2. Then if the pressure is increased further to P3, again the distribution curve has become smaller and it has moved closer to the diagonal line. Okay, so beyond P3, say at pressure P4, you can see the distribution curve is no longer existing. So this happens. So in this case, P3 is critical pressure of either of the component. That means if pressure becomes greater than critical pressure of either of the components, there will be no existence of distribution curve. Distribution curve will not exist. So in this case, P3 is critical pressure of one of the component, and beyond that pressure, if you try to plot, or we can say that distribution curve will not exist. Okay, so in this case, P3 is critical pressure, and beyond critical pressure at for example in this case P4, the distribution curve is not existing. Okay, so in this way we have discussed in this particular short video, I have discussed a different way of representing vapor liquid equilibrium. What is that way? The way is to plot the distribution diagram. Distribution diagram is a plot of mole fractions of more volatile component in liquid and vapor phases. Mole fraction in liquid phase, it is plotted on x-axis. Mole fraction in vapor phase, it is plotted on y-axis. Okay, so you get a curve, and when it lies above the diagonal line, it indicates that vapor phase is rich in more volatile component at equilibrium, and this is essential in order to have successful distillation. Okay, so for obtaining distribution diagram, we are using the tie line data on the boiling point diagram. Every tie line on the boiling point diagram, it becomes a point on the distribution diagram. And finally, we saw what is the effect of increased pressure. Pressure, when it is increased, it affects the distribution diagram. And if pressure becomes greater than critical pressure of either of the component, then the distribution curve will not exist. Okay. So with this, I end my discussion for today. Thank you for being with me. You please do subscribe to my channel and hit the bell icon. Thank you.